All right, welcome to the Explainer. Today, we're going to talk about a number that shouldn't even exist. I mean, for centuries, mathematicians thought it was totally impossible. But this isn't just about solving one tricky problem. This number opens up a whole new dimension of math. So let's take a look at what happens when you step off the number line. Okay, so to get our heads around this, let's start with something we all learned in school, right? The real number line. You know, it's the foundation for pretty much all the math you've ever done. I mean, think about it. This line has everything, right? All the numbers we use every day. Positives, negatives, fractions, you name it. It feels complete. But what if it's not? What if there are some really simple-looking equations that just don't have an answer anywhere on this line? And here it is. This is the troublemaker right here. X squared plus 1 equals 0. Looks so simple, doesn't it? But if you try to solve it, you need to find a number that when you square it gives you -1. And if you stick to the real number line, well, that's just impossible. You can't do it. So this really sets up the big problem, doesn't it? On one side, you've got the rules we've always followed. On the number line, if you square any number, positive or negative, you get a positive result, period. So this equation is a dead end. But then, here comes this wild idea from the other side. What if the rules aren't wrong, they're just incomplete? What if we could literally just invent a number to fix this? And that's exactly what they did. This led to what is, honestly, one of the most creative, mind-bending leaps in the entire history of math. They decided to just imagine a new number into existence. So the solution wasn't found, it was made. It was a total act of invention. Mathematicians basically said, okay, let's create a symbol, we'll call it I, and we'll give it one job, one radical rule, I squared equals -1. This wasn't something they dug up or discovered on the number line. It was a brand new tool they built from scratch. And you gotta love the name they gave it, the imaginary unit. And we have a guy to thank for making this official. The person who really standardized the symbol I was the legendary Swiss mathematician Leonhard Euler, way back in the 1700s. He's the one who gave us the clear, simple notation to actually start working with this wild new idea. And once we have I, suddenly a whole new type of number is possible. It's called the complex number. We usually write it as Z, and it's kind of like a hybrid. It takes a real part, A, and smashes it together with an imaginary part, B, all in one neat package, A plus IB. But here's the kicker. Creating I didn't just give us a new number. Oh no, it gave us a whole new dimension to play in. So, welcome to the complex plane. Seriously, think about it. Before this I thing, the entire universe of numbers was just a flat, one-dimensional line. This one little invention takes us from that line to a whole two-dimensional plane. It's just incredible. This is the magic of what we call the complex plane. Some people call it an Argand diagram, named after a guy who helped make this visual famous. It's got two axes, right? The horizontal one is just our good old real number line. But now we've added a vertical axis, and that's for the imaginary part. So what does this mean? It means we can actually plot these numbers just like finding a spot on a map. A number like 2 plus 4i, that's just the point 2, 4. 2 steps over on the real axis, 4 steps up on the imaginary. What about a number that's purely imaginary, like 5i? Well, that's just 0, 5, straight up the vertical axis. And a regular old real number like -6, it's at -6, 0, sitting right on that horizontal line, exactly where it's always lived. Okay, so we've got this new map, a whole new world. But how does it work? What are the rules? Let's check out the physics of the complex plane. Good news, addition is as easy as it gets. Seriously. You just add the real parts with the real parts and the imaginary parts with their imaginary parts. You keep them in their own lanes. That's it. Simple. All right, multiplication. This is where it gets a little more fun. And the whole thing runs on this really cool repeating pattern that I has. So I to the power of 1 is just I. No surprise there. I squared, as we know, is -1. That's the whole point. Now I cubed, that turns into -I. And then I to the 4th power brings us all the way back to +1. And then it starts over. This little 4-step dance is basically the engine that drives all of complex multiplication. So let's say we want to multiply two of these things. We basically do it just like we would in high school algebra. You distribute everything. We'll take 2 plus 3i and multiply it by 3 minus 2i. And when you multiply all that out, you get this. 6 minus 4i plus 9i minus 6i squared. Now, you got to pay close attention to that last bit, the minus 6i squared. Why? Because we know the rule. I squared is just -1, so that negative 6i squared, it flips and becomes a positive 6. It's like magic. The imaginary part suddenly becomes real. And from there, it's just cleanup. We add the real numbers together, add the imaginary numbers together, and boom, we land on our final answer, 12 plus 5i. See? It's a really elegant, self-contained system. Everything just works. Okay, so why? Why did we go through all that? What's the big payoff? What is the real power of I? I mean, what kind of problems does this new dimension actually help us solve? Let me throw a question at you, and it's going to seem weird. We all know that on the regular number line, the cube root of 1 is, well, it's just 1, right? 1 times 1 times 1 is 1. Easy. But now that we have the complex plane with all its new possibilities, how many cube roots of 1 do you think there are? The answer is 3. Not 1, 3. 3 completely different numbers that when you cube them, all give you the number 1. And here they are. You've got the number 1, the one we all knew about. But then you have these 2 other new complex roots. But the part that will absolutely blow your mind isn't just the numbers themselves, it's the geometry. When you take these 3 roots and plot them as points on the complex plane, they form a perfect equilateral triangle. It's just a beautiful, stunning connection between algebra and geometry that you would never see without complex numbers. So here's the big takeaway. By daring to invent one impossible number, mathematicians did way more than just solve some old pesky equation. They literally unlocked a hidden dimension, a dimension where algebra and geometry are beautifully intertwined. And this isn't just some abstract curiosity. It's become absolutely essential for things like electrical engineering and quantum physics. By creating this new dimension, we solve some of the oldest problems in math. So it really makes you wonder, doesn't it? What other puzzles are out there just waiting for us to find a new way of looking at them?